with that, I'd like to welcome Bassam Salem up to the stage. He's a member of our external advisory committee and the co-founder of Mindshare Ventures and Atlas RTX. And he's just been a wonderful supporter of everything that we're doing here at the RAI.
Does this one work too? I guess that is too leany. Well, thank you everyone for being here. And should I just have Blake and Dee come up now, or Blake and Dee, can I come join me? That way we can all get comfortable being up here on the stage. So.
Oh, and we can actually get.
And will the slide advance automatically, or will?
This one is tricky.
Okay.
So if you're ready, when you're ready.
Well, let me quickly introduce you. Unfortunately, as Penny alluded, Brian is under the weather, but he was kind enough to record this for us. Brian is a faculty fellow, a responsible AI faculty fellow and a professor of anthropology. He's originally from San Francisco, did both his PhD and postdocs at Stanford, and beautifully married his college sweetheart, which is not an embarrassing fact, but a sweet one. And he was gracious enough to do the recording. I'll just let that go, and then we'll continue after that.
Hi, thank you all so much for being here today. I wish I could be there with you in person. Today I'm going to talk about AI-enabled restoration of indigenous ecosystems. We're all used to experiencing environmental crises, from drought leading to the drying Great Salt Lake, then turning to too much rain and we get floods. We end up with dry summers that result in wildfires, and all of this leads to species extinctions. Many of these causes are linked to climate change, but there's another core cause here that is ignored by a lot of science, and that is the removal of indigenous populations from Western North America, from all of the Americas. And that's because these populations were part of these ecosystems. These ecosystems evolved with humans and what they were doing. And so if we really want to restore these ecosystems and avert crises, we need to understand what those past interactions were like and how we might be able to restore them today. One very important example of this is the Bear River Massacre, not too far north of where we are right now, where 450 men, women, and children were murdered by the US government. Today, members of the Northwestern Band of the Shoshone Nation are working to restore this landscape, known as Wood-a-Ogwa, here in the entire Bear River corridor. This project is incredible. Indigenous restoration efforts are clearing invasive water-hungry species, supporting native habitats for endemic species, and sending over 13,000 acre-feet of water back to the Great Salt Lake every year. But how do we scale this up? This is one 350 parcel of land. How can we scale this up to understand the strategies that we might be able to employ, particularly to balance economic trade-offs, when we look at restoring this entire watershed that is the greatest source of water to the Great Salt Lake? AI provides a very important opportunity here because traditional process-based models are too computationally intensive to actually do this. And instead, what we can do is rely on the same information that we have today, for example, the distribution of natural capital like water, soil, and species, particular economic benefits of land, say farmland revenue, or tax benefits from conservation easements. We can then see how land use is dictating those things, whether the land is urban, farm, conservation land. And of course, we can model how climate, both today and into the future, is going to be affecting this. All of this information then can get fed into neural networks, in which case we can train a model to help understand what the optimal scenarios might be if we want to balance, for example, the trade-offs between economic output and restoring natural capital, particularly when this is informed by indigenous practices in restoring these ecosystems. So in this case, we can take an example and we can scale it up across space. We can also apply reinforcement learning to let an agent actually play in this environment and figure out what the best strategies might be. And in the end, what we might end up with are strategies and opportunities to restore indigenous ecosystems enabled by artificial intelligence that allow us to reduce these crises that we're experiencing on a daily basis. Thanks to an incredible team for all of this work. Of course, thanks to the RAI initiative, and thanks to all of you for being here today.
You know, one thing I wanted to quickly say, was I met these three researchers beforehand to prepare, and I knew I'd be really impressed by their intellect. I knew I'd be impressed by their research, but sincerely, I was most impressed by how wonderful as humans they all were. And I congratulations sincerely for selecting such amazing people. So next, we're going to go to Dr. Blake Vernon, who's a postdoctoral fellow with us, and actually Brian is one of his mentors. Blake is originally from the Arkansas River Valley, played baritone in high school. I actually had to Google what baritone was. Sorry to embarrass you. Now I know what it is. That's uh, he approved this embarrassment. I'm I'm a Star Trek fan, not as big as Blake, but I am, and I was surprised that he too likes The Next Generation. I like The Next Generation because Jean-Luc Picard is bald, but a sex symbol. So I'm like, that is awesome. Can we please go back to that? But with that, I will welcome Blake to do his talk on behavioral ecology.
Okay, hi, my name's Blake. I'm a 1U RAI postdoc. My advisors are Simon Brewer in the department formerly known as Geography, and Brian Cotting in the department that's soon to be formally known as Anthropology. Today I want to talk about our research leveraging responsible AI to promote water use efficiency in the Western US. Anyone who has lived out here for any amount of time should already be primed to obsess over the region's water budget. But I think it is worth reminding ourselves of two important hydrological facts about the American West. First, the ratio of water supply to water demand is marginal at best. So if there is any water out there, it will probably get used. And second, the biggest source of demand for water in the West is agriculture. I think current USGS estimates put the fraction of total water withdrawals attributable to agriculture at around 80%. And now complicating those two facts, of course, is the presence of massive uncertainty about the supply of water in a given year. In fact, the Western US is currently in the grips of a multi-decadal drought so severe, one has to go back over 1,000 years to find an event of similar intensity. The challenges raised by the combination of these factors are profound, but they are not insurmountable. One way we can confront them is by leveraging AI to make agriculture more water efficient. And one way we can do that is by helping farmers get a better sense of how water is and will be distributed in the soils that their crops have access to. And that should also hopefully inform their irrigation practices. And this is the focus of my research as a 1U responsible AI postdoc. All right. So this is a Google Earth image here. It shows these center pivot irrigation fields near Meadow, Utah. It's on I-15 if you're familiar with that. While my research isn't restricted to these sorts of irrigation systems, I like to use them as a unit of analysis because A, they are ubiquitous in the American West, and B, they help focus attention on the spatial scale and level of decision-making that a farmer is likely to experience on a regular basis. By far the biggest challenge to modeling soil moisture on plots like these is the availability of data. It's really hard to measure soil moisture. There are two sources of such data. One are monitoring stations that are kind of just scattered across the country. And the other, of course, is orbiting satellites. In addition to differences in precision and accuracy, these two sources offer a familiar trade-off, with stations providing greater temporal resolution but less spatial coverage, and satellite imagery providing greater spatial coverage, but less temporal resolution. So a lot of my work is focused on integrating these data sets with climate and terrain data in a way that balances that trade-off in order to optimize soil moisture estimates at the resolution of these center pivot fields. Okay. Data scientists and statisticians often distinguish between explanatory and predictive models, or models developed to make sense of what has already happened, and models designed to forecast what is going to happen. The AI models I'm developing are trying to do a little of both of those. So here are just two examples. They're not exhaustive, but they are illustrative kind of work I'm doing. The first uses an approach called universal deep kriging, which is an AI version of a standard geostatistical technique. The basic idea is to model a causal and spatial relationship at the same time. The causal relationship being between climate and soil moisture at a given location, and the spatial relationship between soil moisture at one location and soil moisture at another. The combination of the two should give us much better soil estimates on farm plots where that hasn't been measured. The second approach is a lot closer to the sort of image classification problem that people normally associate with AI. The idea here is to take soil moisture forecasts that other research groups have already generated and figure out how to downscale those forecasts to a resolution that's relevant to the farmers. This is done by training an AI model to reconstruct other images like terrain imagery that are already at the desired resolution and are known to be related to the target outcome. That one is still a work in progress, but it's progressing. Okay, so just to give an example, this is an example of what the kriging approach can yield. These are soil moisture estimates for central Utah on June 15th of this year. The model was trained on data over the last, from 2015 to 2020, I think. Right. So just for reference, that thing jutting up in the middle there is the Pavant Range. That means you have Gunnison and Salina in the valley to the east there. Fillmore, apologies. So this is for the Utahns in the room. You have let's see, Gunnison and Salina on the east side of the range. Fillmore and Meadow on the west. And can't really point at it very well. But by far, well, in my opinion, the coolest named town in all of Utah is Scipio there. I believe Utahns call it Scipio with a soft C. It's named after a pioneer who his name was Scipio Africanus Kinner, but he himself was named after the famous Roman general who defeated Hannibal. Okay. Not that that's relevant. The thing to note here is that originally we had soil moisture estimates just at the station locations, but with our AI model, we can estimate soil moisture over a continuous field at any resolution, including that of center pivot fields. Okay. Am I doing all right on time? We have time. Okay, sorry. Okay. So last spring, Simon, Brian, and I worked with Dr. Parashar and other collaborators at SKI to submit a proposal to the collaborations in artificial intelligence and geosciences program at NSF. And so with the remaining time that I don't have, I just want to briefly highlight two projects that we proposed as part of that. One is to look for precursors to drought by modeling soil moisture deficits in the basins around the Great Salt Lake. And then the other is to develop an agentic framework to support decision-making in agriculture and water management. And that one would use the AI models we developed to estimate soil moisture. And that's the part that will be led by Dr. Parashar. I'm really excited about these projects. Still waiting to hear back about whether they get funded. We'll see how that goes. Thank you.
Thank you, Blake. All right. And last but certainly not least is Dr. Di Wang, also postdoctoral fellow, originally from China. He initially did an exchange year here in Ithaca, New York, here being the US, not Utah. Sorry. He climbed, I like to think of this as the abstraction stack, because he studied physics, then electrical engineering, then computer science, and now he's in human-centered computing. So, you know, he's got the whole technical stack. He spends his time chasing his 3-year-old around the local playground and stays fit that way. But wonderful researcher, Dr. Wang.
Hi, hi everyone, and I'm Di Wang, and today I'll share my ongoing research and on like designing AI agents to better understand and support disaster recovery. And my focus is on making like disaster recovery, and making sure recovery is measured based on what is happening like on the ground, what communities are experiencing on the ground, instead of what fits into the official disaster recovery timeline. So when we talk about recovery from environmental hazards, it's about getting communities and places back to where they were before the disaster. Think about the town after a wildfire. Houses rebuilt, business reopened, school back in session. That is recovery, and that could take years. Here's a problem. Like a disaster recovery doesn't always follow a fixed timeline. However, like most funding and policy programs does, most of them ends within like 24 months. And that means support always like often dries up before like a community is fully recovered, while communities are still far from being whole again. And this matters a lot in Utah and across the Mountain West, where we face wildfire and flooding risk a lot. So if we don't align policy timelines with real recovery needs, families and neighborhoods can get left behind. So our work is about helping agencies make better policy recommendations so it can last as long as it's actually needed. So to study this, we bring together a wide range of data, census records, property tax, county business patterns, and also like street level and the satellite imagery, as well as social media activities. And that gives us a multi-dimensional view of disaster recovery. But there are gaps, like rural and low-income areas are often underrepresented in digital traces. So if we don't address those communities, those communities could be overlooked in the model. And this is where we rely on field research to better understand different sub-communities. And of course, like everything we do follows like a strict ethics, like ARB approved studies, anonymization, and agreements with communities about how their data is used. And here is like how the model should work. It is a workflow that combines different agents, like different agents for social media, imagery, official records, and field research into a into a multimodal spatial temporal workflow. And basically, it learns recover patterns across space and time. But building AI like this has risks. That's why we add responsible AI checks. First, the fairness. We adjust for gaps so rural and low-income communities are not invisible. Second, transparency. We publish what signals matter the most, so partners can understand the results instead of treating it as a black box. And third, reliability. We show confidence scores on the flag predictions that are too uncertain to trust. And in other words, we don't just build like an AI agent, we build one with guardrails. Let's look at the Lumberton, North Carolina. And after Hurricane Matthew in 2016, some neighborhoods bounced back, but other neighbors are lagged 6 to 12 months. For example, the non-Hispanic Black communities and Native American Indian communities experience greater loss than non-Hispanic white communities based on the field research that it takes them much longer to recover. And one indicator we tracked was occupied versus abandoned houses. Like FEMA housing aid ended after 18 months, and state and local programs also followed FEMA guidelines. However, like some neighbor needed more time, more than 6 years to recover. As you can see, even after 6 years, the occupied rate is still near as much as what it is before the disaster. And this shows the gap between the short-term aid and the long-term needs, and why better measurements can help agencies target support to places falling behind. So looking forward, we are expanding beyond hurricanes to wildfires and floods. We will be piloting this work with Utah Division of Emergency Management, deploying AI agent in practice. We had conversation with PIOs in State Division of Emergency Management who happen to move to a military base in Tulane. So we are also trying to work with new partners. And as we scale, we are putting safeguards in place, governance boards, bias audits, and careful adoption. And together, we need more partners. We are seeking new data sets, pilot sites, and collaborators. So if you are working on disaster recovery or know communities who might be interested, I'd love to connect. Thank you.
Thank you. Okay, well, that will go to the Q&A section. So hopefully a couple of you will have questions for these researchers, but we'll start with one from me to you, Blake. I'll be the first to admit that it was only as I was preparing for this session that I appreciated the fact that there are two ways of interpreting the expression responsible AI. As a computer scientist, I sort of thought of responsible AI as how we build AI responsibly. Bias mitigation, security, privacy, those sorts of things. And I'm embarrassed to say I didn't really appreciate the other dimension of responsible AI, one we're touching on today, which is how can we use AI to be responsible stewards of our society, of our environment, and so on. And I really love that I gained that appreciation in preparing today. So I'll start with you and have you please address your take on responsible AI as it pertains to your research, your project.
Is this on? Okay. So in environmental data science and in climate modeling in particular, there's this concept of the cascade of uncertainty. You've all heard of this. It's they take different emission scenarios, so how much carbon is going to be emitted over the next however many decades or whatever, and then they use their climate models to project. To project what climate will do in response to those different emission scenarios. And then, so you have each one of those scenarios represents some level of uncertainty about what our carbon emissions will look like. And then within each one of those scenarios, there's uncertainty about how climate will exactly respond to that. And then there's uncertainty about how that climate change will affect regional environmental dynamics. And then there's uncertainty about how that regional environmental dynamic will affect the way that people respond to climate change. And so you have this increasing cascade of uncertainty. And it's something that we've been thinking a lot about since I joined the RAI initiative, is this idea that we could introduce biases into the model in different ways, particularly in the way that we collect data. And those biases could themselves get propagated in unknown ways in our climate simulations. And so trying to think about how we safeguard against that, I think, is an important question. One that we're working on. We have a paper in progress, but yeah, it's early stages for that one. Another big thing is with the issue of data representation in particular, it's not as big an issue if you just look at the United States, because we have the federal government dumped a bunch of money into building monitoring stations and building satellite capacity to measure these things that are important to us, like soil moisture. But when you look at the entire planet, the distribution of all of that equipment looks really different. It's the Northern Hemisphere, and it's basically just Europe and the United States. And so trying to think about how you develop these tools in a way that they can still be useful to people in other countries, I think, an important issue.
Thanks, Blake. Nice win the picture contest with the hat. We'll go to you, Dee. With your research, what would you say is your biggest challenge or obstacle that you're overcoming at the moment?
Yeah, so for me, I think as I mentioned at the end of research, like piloting the research or like deploying like the agent to who actually need it, like to practitioners. I think that is the most challenging part, because I think from our conversation with public information officers, like in either the State Division of Emergency Management or like or the city governments, and or even like the military, like for them, they cannot use any tool, like third-party tools in their work. And if they want to do it, that needs to go through legislation, and they need to apply for external fundings for that. And that could last a really, really long time. But like I think like as we all heard this morning, we'll get good news, like the state like are going to sponsor like, or like they are welcoming like a new like deploying AI for their work. But so things could have changed like within the past 2 years, but it's still like uncertain yet. So I still think there is really a large gap between like our research to like whether it can really like help practitioners make decisions near real time.
Wonderful, thank you. Do we have any questions from the audience for our two researchers? All right. It's always the first one that's hard to get. Oh, we have two. All right. You have one right behind you.
So thanks for the talk. So one question I have when working with spatial data is it's great to put this kind of connect a lot of the other data you have from the environment and geography with where there are actually people in those locations, right? And the challenge with that is that the location of the people, if you're gathering it, it might be something that can leak a lot of information about those. So those individuals, if you can trace someone's GPS trajectory, you know exactly where they live, where they work, you can figure out who's going where. And sometimes you don't want to link that. So what do you think are good ways of blending this kind of data about people in this environmental setting with the information and the sort of predictions you'd like to make?
Yeah. So I think, yeah, that's I don't have an answer for that, but like, so a lot of the mobility data we are getting were from the, let's say, I say original from the GPS or mobile companies where they have already do the anonymization or from their end. So where like the kind of data we have don't have any, well, it's more about like what is happening within this area, and we don't have like a so I don't know whether like the individuals want to leak those information from their end, but like what we are getting from the like the cell phone companies is already like when we are using the data, we already don't have those like individual traces from them. So and since I'm doing this thing like with more like area based aggregation, and I still think like there might be ethical issue with it, but I'm doing this like more like area based aggregation, and I think it would be like uh, mobility data will be like really one aspect of it will be helpful, and but we will try not to like, kind of leak individual information from all of it, and which we don't really have. So
Great question. Thank you.
Hi, probably more for Blake, but both can absolutely answer. A classic problem in machine learning systems is data drift. Your work is a lot about climate and geography and how they interact with each other. The geography is changing, the climate is also changing. How do you think about the importance of drift and monitoring and continuous evolution of your system?
Are you thinking about updating? Like
Yeah,
yeah.
keeping it accurate over time.
Yeah. Actually, this is it gets to another thing that I wanted to mention about responsible AI, and that's just the idea that of making these tools as accessible as possible. And a lot of the complicated AI models require a lot of compute resources, and so millions or tons of parameters that end up getting estimated. And so those end up being really costly, and then trying to make those accessible to people becomes a challenge. There was so a roundabout way to get to your answer in that. There was the Lyft engineers, I think in May, published a little article where they talked about engineering trade-offs between the complicated neural network models and just using simple linear OLS. And one of the things that they pointed out is that, and using like a stack ensemble with the linear models, is that for the sort of time series that they wanted to do, where they needed to have really current, up-to-date analysis of demand, it turned out that just using simple linear models was a more effective strategy because they could update it faster. And so, yeah, I guess the way I think about it, so I guess the idea is to work backwards from the problem, which is these farmers have to irrigate all these plots, and we're thinking about the most efficient way to do that. And then think about the time scale at which that happens. I guess part of the research that we have is thinking about how large of a time scale, like back, you need to look at to understand like the factors that are driving soil moisture. And yeah, I guess that's an active area of research.
Thank you. Any other questions? Do we need a comedian to come up and wake everybody up in the afternoon? Well, with that, oh, great. All right. The comedian is coming, I hope.
Oh, hi, everyone. I have a really basic question. So I'm not coming from engineering or any of those perspectives. I do community engaged learning. So we work with helping faculty connect their courses to work in community and try to solve these large, persistent social issues. So I'm really coming from like a community-based perspective. And one concern I've heard when we've brought up with the Impact 2030 and serve communities is where responsible AI sits. A concern I've heard repeated was the concern about water usage linked to increasing usage of AI. And I'm just wondering if that's something that, we are addressing and how, and, especially as we grow it, like how, and because I kind of was hoping with this particular topic point that maybe it would address some of that. So thanks.
That is an important topic. I'm not as familiar with the research on that and the numbers there. Most of the things I was looking at for this presentation come from the USGS and a report that they released on water availability across the country. And it's mainly trying to estimate water supply and water demand. But they were looking at the previous decade from 2010 to 2020, even though that just came out earlier this year. So I think that's yeah, an important area to look at, definitely.
Answer that from the broader RAI perspective as well. I think when you think about environment and RAI, sorry, I don't know where to stand. But when you think about environment and responsible AI, I think there is kind of a two-factor, right? You're looking at how we can use AI to look into things like environmental resilience and kind of attack some of the problems that you both are looking at. But then you can also look at it at how we can evaluate that impact and kind of look at it longer term. And I think some of this was brought up earlier. I think both Manish and Mitzi kind of touched on this, but I think that there's being a lot of work done to both look at how algorithms are being more efficient over time and how we can kind of reduce the impact of some of these things. And it comes back to that comment earlier about how LLMs aren't all of AI. AI is much broader, and we can do a lot of things to kind of evaluate environmental impact, but also be very positive about the things that AI can do for the environment as well.
Thanks, Penny. Any other questions before we give these folks a big applause? All right. Well, thank you, everyone. Thank you, guys.